Good afternoon, everyone. My name is Amir Asiaee, and I'm a data scientist at Nominum, which is now part of Akamai. Today, I will present the work of our team on behalf of Yuri, Hongdong, and Alexei. The title of my presentation is Augmented Intelligence to Scale Human Fighting Botnets. I know we've heard about malwares quite a bit in the past couple of days, so I'm just going to go with the trend. We're trying to address the problem of too many malwares, but unfortunately too few security researchers to be able to catch them and this growing threat. So I'll talk about how we're scaling up our approach with intelligent machines. I'll focus on 3 key steps that leads us to our destination, and I will show you some real-life examples of how we detect and block botnets with some cool visualizations. So a little bit about Nominum, now part of Akamai, data science and security team. At Nominum, we receive and process about 100 billion DNS queries per day in real time. So quite large scale of data. This data comes from our global partner ISPs around the globe. Mostly, and the majority of data comes from our Vantu cache servers, and it's often anonymized. This data is a sample of roughly 1.5 trillion DNS queries that we're serving per day. So as you can see, we have a good visibility of global data that is the key to solve many of the security problems that we see on the internet. So what is the problem? The main problem is that malwares are moving so fast, they're evolving so fast. The main notion of domain generation algorithms, or DGAs, are running wild out there, and they're almost getting out of control. So we need to find a way to fight them back. In this way, we've seen in the past few years that the lifetime of malware and CNCs is becoming shorter and shorter, and we've seen campaigns that come for just a few hours and last, and they're gone, and we don't see a trail of them anymore. Similarly, for malicious ad campaigns, they've become very short-lived, and they're everywhere. So on the right side, you can see a bunch of domain names. I'm not sure if you can clearly see it, but if you can see, please let me know if they're part of any malwares, because we tag them as malicious, but they're not part of any known malwares. So if you could let us know, that would be great. So the traditional approach is to do reverse engineering, but it's not enough due to the fast growth of the threats that we see. They move too fast, and we don't have enough security researchers to detect them and block them. So our solution is to scale up the human power and intelligence by machines. So in our approach, we focus on 3 keys in order to unlock the magic box of threats. The first key would be our correlation engine. So we build something called a correlation engine that is built using the real-time DNS traffic. We build a machine learning model based on that. And we see a lot of new domains every day. And we try to capture them in real time and keep track of them. That's the second key of our approach. And the third key is our clustering. The new domains that comes to us, we're trying to find a way to cluster them and detect them as malwares. In addition to that, we enhance our approach with the security community and our third-party partners that helps us in labeling the threats and the specifically botnets that we detect. As a result, we're going to have an enriched threat intelligence that will serve our customers and secure them in a very quick time. So our correlation engine, the main goal is to be able to represent all domain names that come through our DNS traffic in order to calculate some sort of correlation between them. So we can later on cluster and group them together. Our approach is inspired by word2vec, which is widely used in natural language processing. So the key is to be able to maximize the co-occurrence probability of the DNS query sequence that we get. So let's say for every 10 minutes, we try to rebuild our model based on a, say, 10-minute snapshot of the global DNS traffic. And then using that, we will try to do the clustering later. The benefits of this approach is that it's very robust against noise. For example, the legitimate domains will show very low correlation to malicious domains, which is the goal that we're after. So the model that we built is going to be both sensitive to high rank, such as like very high ranked domains out there, and long tail domains that we see quite a few of them in the traffic. And the main benefit of our approach is that there's no requirement for predefined knowledge. So we just learn from everything that comes through our DNS traffic. So how do we learn these representations? As I said, the input we can assume to be the DNS sequence that we get from each client IP. So every user will have a number of DNS queries as they use internet over time. And then what we do, we get each domain name. We convert it to some sort of a binary vector. Specifically in our approach, we use Huffman coding for that. Based on that, we feed these. So for every domain name, we build a vector, and we feed these vectors into our neural network to learn the weights and to build a model by maximizing the co-occurrence probability of the neighborhood, like what domains appear in the neighborhood of a certain domain at certain time, with some moving so-called windows. So, and at the end, the output of our model will be the vectors with hundreds of dimensions. So for each domain name, we will have a vector of hundreds of dimensions, and each dimension embeds a numerical value as which is a floating point. So what do we do with this? The correlations, after we represent every domain with a vector, then we have a mathematical problem to solve. If you want to find a correlation between two vectors, just do the dot product, and there you have a score that will give you how much correlation exists between every two domain names that we see. So as I mentioned earlier, and I emphasize, there's no prior knowledge. And what we do in correlation is not a string similarity. And we don't need or use any manual feature engineering. So now we have the first key to unlock our threat intelligence, which is the correlations. In the second step, we see that the majority of the new threats come from new domains that every day appear in the DNS traffic, specifically core domains. How do we define core domains in our work? We define core domains as the second part to the TLD of a FQDN. For example, Nominum.com or Akamai.com. So the second definition is what do we define as a new core domain? Anything that we see in our traffic that we haven't seen before is called a new core domain. This core domain is not necessarily registered anywhere. It might be registered or might not. It might be just like randomly generated from a DGA. So we build a system at Nominum that tracks these new core domains in real time. And as you can see on the right side, with a unfortunately low resolution, this is a dashboard that we keep track of, and it's just cool visualization for the executives. So there we have it, the second key for our magic box. So using the correlation engine that we have, we build a numerical vector for every new core domain that we get in real time in this step. There was quite a bit of engineering challenge to be able to capture these core domains in real time, because we have approximately 100 billion. After filtering out 1.5 trillion, we still have 100 billion queries per day to go through. It's quite a bit of it's a large number to keep track on a global base. So, and these queries comes from our partners, partners from multiple locations in the globe. So our solution is that we feed this and we ingest all these through our Kafka data stream from all our partner carriers. And we use a combination of open source tools with some in-house solutions to be able to handle and keep track of every new domain that appears in our traffic. The third part of our approach is called as clustering. So we have let's assume we can find the correlated domains. Now what do we do with it? We now have, for each core domain, we have a vector of numerical, a numerical vector that we can use in clustering. We use spectral clustering with very few threshold parameters. The reason we use spectral clustering is that because we experience, and this method gives us the clusters with the most density that is appealing for us. So again, for our executives, we build a fancy visualization tool, which I don't know if I can show it here. Yeah, there it is. So every core domain, which is 100 of dimensions, we reduce it with tsne to 3 dimension, and we use this visualization tool to show the clusters that are forming here. So as you can see, here we have the necros with here another one. It's a 0-day cluster with which is kind of unknown. Nobody has seen it before. Here's another one. So this is the part that we can see. Okay, let's move on to the, okay, here. So so as I said earlier, we were trying to scale up the threat intelligence. I'm going to show you a few use cases of that we were able to detect and block with our approach in the next few slides. So we have sometimes we have only a few domains that are reported by the third parties. We can add more coverage to that by finding clusters that have high correlation with those domains. We can detect a lot of DGA-based botnets, and sometimes some DGAs, some new botnets comes with some sort of variation of old DGAs, which is not yet reverse engineered. So we would, there are cases that we detect them, but there's no reverse engineered effort of that yet. So we block it before everyone else could reverse engineer it. And at the end, I'll show you an example of fileless malware, where there's no, where there's not even a binary code to reverse engineer that. So as I mentioned earlier, sometimes malicious ad campaigns are common, and we see a few of them reported by our third parties. We try to come and match them with our, we find clusters that include them, and when we see clusters with good density that includes them, we go ahead and with high confidence block the rest of the correlated domains that we see. So I think everyone can see that all these other members look pretty malicious. The next example, sometimes we know the DGA. An example is Bedep, and which is a financial fraud, but it changes the seeds frequently. So it's hard to get the seeds and predict the CNC. But when we find clusters that include those seeds, it can be blocked with high confidence as a botnet. Another example is Virut that has too many seeds. So Virut, as you might know, has a generates domains with the length of 6 characters, and it could lead to very high collision with legitimate domains. As you can see there, I have an example of somebody reported this domain Dawn as malicious, which is a false positive, but it fits the profile of this DGA. Even a name like Asiaee.com fit this profile, but should we block him? No. What we do is to find proper clusters that allows us to block these with high confidence. So a domain like Asiaee have a very long history. It's not a new core, it's not a new domain, so we know that it shouldn't be blocked. But as you can see, the rest of these domains that appeared here are all new, and they look pretty malicious, and they have the same behavior as botnets, so we block them. Another example is Suppobox, which is a dictionary-based DGA. So the so-called vanilla Suppobox uses one English and one person names dictionary words to generate domains with .NET TLD. But earlier in 2016, we detected a new trend with .ru domains, which is also a mix of dictionary. At the time, we did not find any reverse engineered DGA or known DGA for that. And then we blocked them earlier in 2016 because we realized that all these new core domains have the same behavior of not being resolved into anything, and it looks like an old variant of an existing DGA. Later on, the 360 NetLab reverse engineered that and published the result in late 2016. So as you can see, this is an example of capturing a DGA before it's been known and protecting the customers. Another example is zero-day clusters. It's not a known DGA, and again, it showed the same behavior as the botnets, and weeks after we detected this cluster and we blocked it, security companies announced it and named it as dorkbot. So it's not a real DGA, but pre-generated CNC lists. So okay, I think I have, yeah, this is the last example I have, which we've found recently. We call it guilty by association because we found correlated malicious domains that already exist being highly correlated with the new ones that we found. So this is found on July 18, 2017. We blocked it on the same day because we had high confidence that these are malicious. Later on, they were confirmed as fileless malware, and in August 15, almost should be a month later. We have a blog post about this one. So to summarize our 3 key steps, as I mentioned earlier, we have at the first step, we have our correlation engine that is being built using the real-time DNS data that we get from around the globe. We also keep track of all the new core domains because of our high visibility of the internet traffic. And the result is clusters of malicious activities that we can detect even before any other company could name them. To summarize, we know that static and dynamic analysis can provide a gold threat intelligence, but unfortunately, it's not enough. New threats are too dynamic to stick to the traditional approaches to fix them. So we're proposing machine intelligence to scale up and be able to detect these trends faster and block them. As I mentioned, we have the 3 key steps, the correlation engine, the new core domain concept, and clustering and labeling, which is the intelligence that comes from the other members of the security community that helps us in our method. So at the end, we realized that there are way more machines out there in the world than human security researchers. So why not lose them? Thank you.
Thank you for the talk, Amir. Are there any questions? Go ahead, gentlemen.
Thank you, Amir, for the talk. Do you hear me?
Yes, yeah.
If I get it correctly, the input for your algorithm is a list of third feeds and domains that they already know that are malicious. This is the ground truth. And you're using clusters in order to find new malicious domains. I was wondering about the coverage results. Do you know what's your unique contribution? Like how many additional malicious domain is the algorithm capable of finding?
Yes. So as I said earlier, we have a very global visibility of the DNS traffic. So security lists that are released are usually identify a botnet or a threat late. So one of the main contributions is that we have a real-time mechanism to detect these threats and stop them before we even know a name of a malicious botnet or cluster. So that's one of our main contributions. Was that the first part of your question, or does that suffice? Okay.
Thanks. There is another question up there.
Hello. Working?
Yeah.
Yeah. I've got more of an operational question.
Could you speak louder?
Yeah.
Thank you.
My question is more operational. When you say you're blocking domains, do you mean that you return non-existent domain responses?
I didn't follow that, sorry.
When you say you're blocking domains,
yes.
Does that mean you're responding non-existent domain to
No,
any request you get?
Yes, so our products that we sell to ISPs, we sell them mechanisms to block them from, to block the threats that we identify from, after we identify them, we block them through the DNS cache servers. So that's where we stop the attacks. Was that the?
So that means whether the actor changes DNS services, you would still be blocking?
Yes.
Okay.
So the customers of that ISP would not be infected further on after we detect and block them.
Thanks. Is there any other question? No? So thank you, Amir.
Thank you.